Okay, I'm going to talk about chemodynamic modeling of the Milky Way and its applications. And I'd like to thank my collaborators, Michael, Jaws, and the GALAH team. So you've heard that Milky Way is like a lab for understanding galaxy formation. What we mean by this is that we would like to understand external galaxies by building upon what we learn from our Milky Way. In order to do this, you need a model that can explain the kinematics, age, abundance of stars in the Milky Way. And this model should be physical rather than empirical. That is, it should incorporate as many physical processes that govern the evolution of the Milky Way as possible. Now, in a nutshell, what this means is we are linking properties of the galaxies to physical processes. And what kind of physical process that happen? The main ones are like secular evolution, which is like the increase of velocity dispersion with age due to scattering, radial migration of the stars, chemical evolution, like Michael talked about, like a buildup of elements due to, for example, supernovas and AGB stars and so on. So, although we have made tremendous progress, but there are still a few things that are difficult to explain. One of this is the origin of the thick disk. If you plot the alpha over Fe distribution of stars in the solar neighborhood, as shown here, you can see there are like these two groups with a valley in between. The high alpha stars belong to the thick disk, which is the puffier component of the disk. Now, it has been thought that this might be due to a pause in star formation, or the thick disk might be due to accretion of an external galaxy. So if you plot these alpha over Fe distributions at different galactic locations, we have R on the bottom here and Z in this direction. So this is above the plane, and this is the inner galaxy, and this is the outer galaxy. And you can see this plot changes shape with location. Specifically, the double sequence is clear in these two panels, but it's only single sequence over here. If you specifically focus on the upper slices, you can see these are thick disk stars, but in the inner galaxy, it is high alpha as expected, but as you go towards the outer disk, it becomes low alpha. So, in fact, this plot involves the interplay of a number of physical processes, and it is rather challenging for a model to explain. And our aim is to develop a chemodynamical model that can reproduce this. So now I'll describe the model. The two main intrinsic variables of the model are age and its birth radius. In fact, most properties of stars can be predicted just from these two. The star formation history, which is the age distribution, rises early on and then gently falls over. As for the structure of the disk, we assume an exponential disk, but the scale length is allowed to grow with time. So we have an inside-out formation. For chemical evolution, we start with physically motivated functions and fit them to the GALAH data. For a purely physical chemical model, there's a poster by Bob and Chen that I would suggest people to see. Now, imagine stars that are born at a particular birth radius. How would the distribution of those stars look now? Well, first thing that will happen is radial migration that will lead to a spread in angular momentum. But if you focus on stars with a given angular momentum, they would have a distribution in Z as well as in R. Okay. And this distribution, the scatter, is governed by the velocity dispersion. Now that brings to the question, what determines the velocity dispersion of stars in the Milky Way? And what are the relations governing them? Typically, velocity dispersions has been studied as a function of age. We know it is due to scattering and so on from spiral arms and giant molecular clouds. But it turns out this is a four-variable problem. There's additional dependence on angular momentum, metallicity, and height above the plane. Now, metallicity, as Michael talked about, at a given age, metallicity tracks birth radius. Now, we came up with a simple multiplicatively separable functional form. What it means is that the dependence of one variable is independent of the other, and they are related by a product form. We use four different data sets. Two are from the Lamont spectroscopic survey, two from GALAH. We also use different scalar types having independent age estimates. For example, two were main sequence turn of star samples, and two were red giants using astroseismology. Now, to visualize this multivariable problem, when you want to study the dependence of dispersion on one variable, what we do is we divide out the dependence of other variables. For example, if you want to study from dependence on age, the ones colored in blue here are other variables, and we just divide them out. Now, these are the results. The top panel shows you vertical dispersion. The bottom panel shows you the radial dispersion. The first column is showing the dependence on angular momentum L. And you can see there is a fall, but for VZ, there is also a rise at high L. With age, you see a monotonic rise. With FEH, you see a fall, almost linear, and with Z also a slight rise. But the important thing to note is different surveys, different age estimators, they agree with each other. That means the results are quite robust. And the old and the young stars, be they on thin disk or thick disk, they all lie on the same relation. Now, some of the trends were expected, like the fall with L and the rise with age, but some others were not. And one of them is this rise with L over here. And this is most likely due to orbiting satellites, which excite vertical perturbations in the outer disk, where the self-gravity is less. The fall with FEH over here, again, remember FEH tracks the Earth's radius. So this is telling us about migration. That is, during migration, the vertical action is conserved, and also the fact that kinematically colder stars migrate more efficiently. And the rise with Z is most likely due to the fact that the disk is not in equilibrium, but it's still not well understood. Now to the chemical evolution. So these are, here I'm showing the evolution of metallicity and alpha as a function of age. Each line here corresponds to a unique birth radius. Let's focus on the solar radius shown by red. You can see the metallicity rises with time and then flattens off. As for alpha, it starts high and then it falls off and flattens. Now the sharp fall of alpha is most likely due to the time delay between star formation and the onset of supernova 1A. We use GALAH data to constrain this model. Now coming to the predictions of the model. This is prediction of the model in the solar annulus. And you can clearly see there are two sequences over here, the high alpha sequence and the low alpha sequence with a valley in between. Now, in order to understand this plot, I think it's best to overlay some evolutionary tracks for different birth radius. So that's basically saying at a given birth radius, each line represents a particular birth radius, how alpha changes with FEH. And it's shown here. This is the inner galaxy with a birth radius of 1, slowly moving outwards, and this is 14 kpc over here.
2 minutes.
Okay, and what you see here is the dots denote the different time intervals. Okay, the high alpha sequence, which is the sequence over here, is basically a sequence of age of stars born in the inner disk, while the low alpha sequence is basically a sequence of different birth radius. And the valley out here is basically due to the sharp transition of alpha with time, and it has nothing to do with star formation, pause in star formation rate. Now, this is the data at different RNZ locations, and this is a prediction of the model. I'll flick a few times. What you will notice is that the data does a pretty good job of reproducing, the model does a good job of reproducing the data. There are some subtle differences, but overall, I think the major trends and characteristics or structures are correctly reproduced. I'll just focus on one particular aspect. Like the top slice that I talked about earlier, and you can see in the inner disk it's high alpha, and as you go out, as we saw in the data, the outer disk is low alpha. Now in our model we know why it is, and it is because of the flaring of the disk, and the flaring is because of this rise of L at high L, the rise of sigma Z with L. So this is how we have tried to link physical process to actually properties of the galaxies. Now, if you don't put in radial migration, you get something like this, which doesn't look like the data at all. Most of the stars are confined to narrow evolutionary tracks, which are the local birth tracks for those stars. The low alpha sequence is not spread out as it is in the data. This highlights the importance of radial migration. And that brings to my conclusions. So what I've shown is that there is a simple chemical evolution model that can explain the abundance maps at different R and Z locations. I've talked about fundamental relations for velocity dispersion of stars. And for future applications, I think the power of this is that we can now link observed properties to physical processes. So this provides a framework to interpret observations of external galaxies. Do I have 30 seconds?
Yeah, go for it.
Okay, this final plot, I didn't get time to go over this, but there's an additional result that we got If you plot angular momentum as a function of metallicity for high alpha stars and low alpha stars, these are low alpha, these are high alpha, and you can see there's a slope or a gradient. Now, for the low alpha stars, we understand why this gradient is there, because these stars were born in the outer disk, they're metal poor, they have high angular momentum. But for the high alpha stars, the trend is reversed, and it's not clear why that happens. And in our model, what we found was, if you assume that the potential changes with time, that the circular velocity increases with time at a given radius, then you can explain a little bit of this. You can see the dashed lines are model predictions, which kind of go down, although it doesn't match perfectly. But this is quite interesting that it says that from kinematics and abundances, you can actually probe the gravitational potential, the evolution of gravitational potential. Okay, that's all.
Thank you. So do we have any questions? Okay, so I was wondering how, so if you could say something about the formation of thin and thick disk.
Yeah, so in our framework, what it seems is that the thick disk and thin disk, there's no distinct difference between them. It's just a continuation of the Milky Way. So it's basically when the stars were born. Thick disk stars were probably born in the inner galaxy, and they have migrated to the solar neighborhood, right? But in terms of star formation history of the galaxy, there is no break. In terms of the relations, they all seem to smoothly vary. So there's no break or discontinuity in any thing. It suggests that it's just normal evolution.
Josh, do you want to?
Just a quick question. Sanjib has this well-used model, Galaxia, which gets used by many survey teams around the world, Gaia team in particular. The question is, with this modeling, will you update Galaxia or make a whole new code available to people who want to model the Milky Way and compare to surveys?
Yeah, I mean, with Galaxia was developed on Bayes song, which was a very different style of modeling, and with new data and everything, things have changed quite a lot. We know migration is important, predicting abundance is important. So I think it's time to kind of update the whole framework of how we model the galaxy. So I might try to update the Galaxia, not update, but rewrite a new code given these changes in mind.